By 2050, the global population will demand a staggering 60% increase in food production, yet the arable land available to grow it is rapidly shrinking. The traditional methods of farming, reliant on broad strokes and historical intuition, are no longer sufficient to meet this impending crisis. Artificial intelligence is stepping out of the data centers and into the soil, fundamentally rewriting the rules of global agriculture. We are witnessing the dawn of precision agriculture, a paradigm shift where algorithms and sensors replace guesswork with granular plant-by-plant certainty. This is not a futuristic concept, but an immediate operational reality transforming how humanity sustains itself. At the heart of this agricultural revolution is computer vision, a field of artificial intelligence that enables computers and systems to derive meaningful information from digital images, videos, and other visual inputs. Think of it as giving machines the ability to see and interpret the physical world. In the context of a farm, computer vision algorithms process millions of pixels captured by cameras to distinguish between a healthy crop, a nutrient-deficient leaf, or a devastating weed. These systems are trained on vast data sets of agricultural imagery, allowing them to recognize patterns invisible to the human eye. By translating visual data into actionable metrics, farmers can address issues at the microscopic level before they devastate an entire harvest. Imagine a drone sweeping across a 1,000-acre cornfield capturing high-resolution images of every single stalk. The AI analyzes this visual feed in real time, instantly identifying a localized outbreak of rust fungus that has only just begun to spread. Instead of preemptively spraying the entire field with expensive and environmentally taxing chemicals, the farmer receives a precise set of coordinates. A targeted intervention is deployed, neutralizing the threat while saving thousands of dollars in chemical costs and preserving the surrounding soil health. This micromanagement of resources is the defining characteristic of modern crop yield optimization. This shift from reactive to proactive farming changes the fundamental economics of agriculture. By treating a massive field not as a single uniform entity, but as millions of individual data points, agricultural businesses are drastically reducing their input costs. The days of applying water, fertilizer, and pesticides uniformly across varied terrain are ending. The financial margins in farming are notoriously thin, and the ability to optimize these inputs through intelligent visual analysis provides a critical competitive advantage. The return on investment for these AI systems is realized not just in higher yields, but in profound operational efficiency. The visual data does not operate in isolation. It is continuously cross-referenced with information from IoT sensors. The Internet of Things refers to a network of interconnected physical devices that collect and exchange data. These sensors, embedded deep in the soil, monitor moisture levels, temperature fluctuations, and nitrogen content minute by minute. When combined with the overhead visual analysis from drones, the artificial intelligence forms a comprehensive, multidimensional model of the farm's ecosystem. This fusion of above-ground imagery and below-ground metrics allows the system to predict exactly what a specific patch of soil needs to maximize its output. The impact of this interconnected data network is most evident in irrigation management. Water scarcity is a critical global challenge, and traditional agriculture is one of its largest consumers. AI-powered systems process the combined sensor and visual data to optimize irrigation schedules with unprecedented precision. Water is delivered only to the specific zones that require it exactly when they need it, and in the precise volume necessary for optimal growth. This intelligent distribution drastically reduces water waste, ensuring that farms can maintain high crop yields even in regions facing severe drought conditions. The translation of this digital intelligence into physical action is brilliantly demonstrated by John Deere and their deployment of autonomous tractors. These machines are not merely self-driving vehicles, they are mobile data centers equipped with advanced computer vision arrays and heavy-duty processing power. As an autonomous tractor navigates a field, its cameras scan the ground ahead, identifying weeds interspersed among the crops. In a fraction of a second, the onboard AI triggers a targeted microburst of herbicide, hitting only the weed and sparing the valuable plant. This capability fundamentally alters the mechanics of field maintenance. Industry analysts note that this level of robotic precision represents the ultimate convergence of software and heavy machinery. The autonomous systems operate around the clock, unaffected by human fatigue or poor visibility, continuously refining their models with every acre they cover. They precisely plant seeds at optimal depths based on real-time soil analysis and harvest crops with minimal damage. The efficiency gains are exponential, allowing a single operator to manage a fleet of autonomous machines from a centralized dashboard, redefining the concept of farm labor. Yet, integrating these sophisticated technologies into traditional farming environments presents significant logistical hurdles. Rural areas often lack the robust broadband infrastructure required to transmit the massive datasets generated by high-resolution cameras and sensor networks. To counter this, AI developers are increasingly relying on edge computing, where the data processing occurs directly on the drone or tractor itself, rather than relying on a continuous connection to a distant cloud server. This ensures that critical decisions like identifying a pest or adjusting a planter happen instantaneously, regardless of internet connectivity. As edge computing matures, the agricultural landscape will transition toward fully autonomous, closed-loop ecosystems. We are moving toward a future driven by generative AI, systems capable of creating new data, models, and predictive scenarios based on learned patterns. These models will simulate entire growing seasons before a single seed is planted. By ingesting decades of historical weather data, current climate forecasts, and real-time soil conditions, they will generate optimal planting strategies. Farmers will no longer just react to the weather. They will execute highly complex, AI-generated game plans designed to mitigate risk and maximize yield under any scenario. The implications of these predictive models extend far beyond the borders of individual farms, directly addressing the looming specter of global food insecurity. By maximizing the output of existing arable land, we reduce the pressure to deforest vital ecosystems for agricultural expansion. Precision agriculture allows humanity to produce more calories with fewer resources, decoupling agricultural growth from environmental degradation. The algorithmic optimization of crop yields is not just a business tool, it is a critical mechanism for planetary sustainability. Large language models, advanced AI systems trained on vast amounts of text data to understand and generate human-like language, are also entering the agricultural fray. These systems act as intelligent agronomic advisors. A farmer can query an interface about a sudden drop in soil nitrogen, and the model will instantly synthesize data from local sensors, historical crop performance, and global agricultural research to provide a plain language, actionable recommendation. This democratizes access to expert-level agronomic knowledge, empowering farmers of all scales to make data-driven decisions. The democratization of this knowledge is accelerating a broader market consolidation in ag tech. Legacy agricultural companies are rapidly acquiring AI startups, blending century-old mechanical engineering with cutting-edge machine learning. This fusion is creating comprehensive digital platforms where seed genetics, chemical applications, and machinery operations are all orchestrated by a single overarching artificial intelligence. The farm is no longer just a piece of land. It is a highly integrated, data-driven manufacturing facility. However, this rapid digitization raises crucial questions about data ownership and operational autonomy. As farms become increasingly reliant on proprietary algorithms and closed digital ecosystems, concerns emerge regarding who controls the vast amounts of agronomic data being generated. The power dynamics within the agricultural supply chain are shifting toward the technology providers who hold the keys to the predictive models. Ensuring transparent data practices and maintaining farmer sovereignty over their own operational metrics will be essential to building trust in these new systems. Despite these complex dynamics, the immediate operational benefits continue to drive aggressive adoption. The ability to forecast yield outcomes with high accuracy completely transforms supply chain logistics and commodity trading. Processors and distributors can anticipate harvest volumes weeks in advance, optimizing their transportation networks and reducing food spoilage before it reaches the market. The efficiency generated by computer vision in the field cascades through the entire global food system, stabilizing prices and reducing catastrophic waste. Looking ahead, the synergy between computer vision and advanced robotics will yield even more specialized applications. We will see the deployment of micro-robots, barely larger than insects, navigating the crop canopy to monitor individual flower pollination or applying targeted nutrients directly to a plant's vascular system. The resolution of precision agriculture will continue to magnify, zooming in from the field level to the plant level and eventually to the molecular level. The boundaries of what is biologically possible will be redefined by what is computationally achievable. The integration of artificial intelligence into agriculture represents one of the most profound technological adaptations of our time. By harnessing computer vision, interconnected sensors, and predictive analytics, we are transforming farming from a battle against the elements into a synchronized dance with data. The challenges of a changing climate and a growing population are formidable, but the tools to overcome them are already at work in the fields. The future of food is being written in code, and the harvest it promises will sustain generations to come.